because these are kind of involved. We don't want to do too many. There's just not much time. So on problem B, let's see what we have. Again, we start out with the left-hand side, which is a series. We've got 3 plus 9 plus 27 plus all the way up to 3 to the n. That means we've got a geometric series because each term we're multiplying by another 3. On the right-hand side, we've got that when you add up all those terms for your geometric series, you will get 1/2 times 3 to the n plus 1 minus 3. Okay, so we're going to prove this using mathematical induction. Mathematical induction says start with step 1, which says let's just try it for n equals 1. Well, if you plug in 1 for n, that means on the left-hand side, we'll only get up to 3 to the first power, which is just 3. Plugging in a 1 on the right-hand side, we'll put a 1 in for n, and we'll get a, if you simplify this piece, 3 to the second, or 3 squared, which is 9. Continuing right along, again, we got to play around with both sides here. The only thing you can simplify on the right-hand side is the 9 minus 3, the parentheses, which will give you 6. Then we would have to say, well, we are taking half of that 6, which is 3. Well, notice, if you compare the left-hand and right-hand sides now, they are the same. So this is going to work. Yes, it is true. At least this tells us it's true for n equals 1. Step 2 of mathematical induction says, okay, let's look at the kth term. So we're going to go up to, instead of 3 to the n, we're going to go up to 3 to the k here. And instead of the 1/2 3 to the n plus 1, we'll do 3 to the k plus 1 minus 3. And again, mathematical induction says, we don't know if it's true, but let's assume it's true. Let's take it as fact. Then we've got to look at the k plus 1 term, meaning instead of stopping at k, we're going to go one term above that. So normally the sum goes 3 plus 9 plus so on and so forth up to 3k. We're going to go one piece past that and add a 3 to the k plus 1. On the right-hand side, we normally go up to the kth power, k plus 1. Well, we're going to plug in for that k. We're going up to k plus 1 this time, so we'll plug in for that k. We'll plug in a k plus 1. Notice, remember there was still the other plus 1 on the outside, so we'll still have that. And the minus 3 and the 1/2 will all still be there. Now we want to use the kth term, the statement that we're assuming is true, our little starred equation, to kind of play around with both sides of the equation. So what that does is it lets us replace the left-hand side, the 3 plus 9 plus all the way up to 3 to the k, this piece here, with whatever's on the right-hand side, which is this 1/2 times 3 to the k plus 1 minus 3. So we can replace that whole thing with the right-hand side, the 1/2, 3 to the k plus 1 minus 3, just using that starred equation. Using that starred equation. And it's because we assume that that starred guy was true. Okay. How does that help us? Well, we have to keep on playing with this until we get both sides are the same. Well, the first thing that I see over here is on the left-hand side, I see parentheses. So let's go ahead and get rid of them. Let's distribute. So we'll get a 1/2 times the 3 to the k plus 1 minus a 1/2 times the 3. So what it does is just multiply that 1/2 out. So we get a 1/2 on both of these terms, which you can see is in the next line. We're getting there. Now the question is, can I combine anything here? And we can. We actually have two like terms. Where are they? We've got a 1/2, 3 to the k plus 1. And we do have another one of these. We have another 3 to the k plus 1. You don't see it out in front, but how many of these 3 to the k plus 1s do we have? We have only one of them. So we're going to add the 1 here and the 1/2 from the other one. Well, if you add the 1 and the 1/2, you get a common denominator, you'll get 3/2. So these two pieces will come together to become 3/2 of these 3 to the k plus 1s. Now, the other piece that's in that left-hand side has not gotten touched. The minus 1/2 times 3, that has not gotten touched. So we're just going to leave it as is. Now the question is, can I make it look like it does on the right-hand side? Well, notice on the right-hand side, it has a 1/2 out in front, meaning it's been factored out. So let's do that on the left. Now that we've combined some stuff, let's pull out the 1/2 again. So we can factor out that 1/2 out in front. That's what we're going to do here. The question is, what's left? Well, notice, what do you have that'll be left? You've got a 3. Notice you still have that 3 term. The problem is what happens here. Well, you've got a 3. That's a 3 to the first power and a 3 to the k plus 1. Those have the same base. Notice they both have a base of 3. So if you have a base of 3 on both of them and you're multiplying like you are here, what can you do to the exponents if you have the same base and you're multiplying? You add the exponents. So you'll take the 1 and the k plus 1 and you'll add them. Well, if you add 1 and k plus 1, you can only add the like terms, which is the 2 1s, which will become actually a k plus 2. So when we combine here the 3 and the 3 to the k plus 1, it actually becomes 3 to the k plus 2. So that will be our second piece that also has a 1/2. Now zoom out. Look at what you came up with for the left-hand side and compare it to the right-hand side. Let's compare the two, and what do you notice? They are identical. They are the same. So what does this mean? It means that we have now proved this is true for, well, we proved it was true for one past what we were looking at, which is the k plus 1 term. And that's all that's required in mathematical induction, is you have proved it is true for the k plus 1 term. So it will be true for any n that you choose. I was just kidding before. There's one more